Okay, folks, here we go with week 5. I've got 3 problems teed up for us this week to go through very quickly. 10-7, 10-11, and 10-21. 10-7 and 10-21 appear to be algorithmic. So just as a reminder, the numbers that you'll see when you get to your problem will be different from this. However, the modeling will not change. So let's get to it. 10-7 is a power distribution problem. So let's see, there's power generation opportunities here: Los Angeles, Tulsa, and Seattle. And then there are cities to which the power needs to be distributed. In the matrix here, in the dollar values, this is the amount per megawatt to transport or to distribute power from Los Angeles to so on and so forth, Tulsa, Seattle, so on and so forth. Over on the far right-hand side, these are the demands. So Seattle needs 950 megawatts, so on and so forth. So there's 2 problems here, and what I've done here is I've set up both problems for you here, and I'll explain the difference based on the statements of the problems. The first one says just simply minimize the cost of getting power to each one of these cities from the potential distribution sources. So the way I have set up my decision variables in this case is I basically just mirrored this matrix minus the demand. I'll show you what I've done there in a second. So this effectively mirrors the dollar piece above, and then I have just replicated the dollar matrix plus the demand over here on the right. So my decision variables are, in this case, is, and again, it's simply how many megawatts are being distributed from LA to Seattle, so on and so forth. So there's about 30 decision variables here. I'll just put them in a matrix, and I think it's easier since that's the way the dollars are presented. From an objective standpoint, again, we're trying to minimize the cost of getting the amount of power we need to each city. Notice that here I have just summed. These are going to be the number of megawatts received. I'm just summing across each row the number that will be received at each city. And then the objective function, our old friend, the sum product. So I've taken the sum product of the decision variables and the costs, and that is being minimized. The only constraint at this point is making sure that each city gets the amount of power that it needs. So the computed values here actually mirror the megawatts received. So I think I actually put in there, and again, as I have before, I'll give you this spreadsheet. So what I did is I just said, well, the computed value is basically just the sum of what's happening in cell H30. So here I just said H30, and then I just copied this all the way down, which pulls all these values down. And so that should work out just fine. So I'll leave that one for you. What I'm going to do is I'm going to set up this one, and I'll show you the solver setup. There's just one more step here. It's the same problem, but then it's further constrained by the fact that if at most 4,000 megawatts of power can be supplied by any one of the power plants. So what we have to be cognizant of here is that LA, Tulsa, and Seattle only ship a maximum of 4,000 megawatts. And what you'll see over in this particular problem is that is exceeded, but we're going to add a constraint here. So what I've done is I've gone down the columns and I have summed all the number of megawatts that will be shipped from each of these cities to the other 10. And then I've effectively just added one more constraint saying the number of megawatts provided from each one of these cities must be less than or equal to 4,000 megawatts. So let's just quickly look at the setup for the second problem here. Let's see, I think I actually have already got this one set up for you. So the objective function is in Q42. That's going to be minimized. And again, it's just the sum product. You'll see the formula. It's just the sum product of the decision variables and the unit costs from each city. That's going to be minimized. The decision variables R30 to R39, which are these cells right here. And then I have the 2 constraints. I have the minimums required for the 10 or 11 cities that we have here. That is, let's see, this top one. So let's see, 45 through 54 is the demand at each city, and then the restrictions on the distribution points less than or equal to 4,000. When I go ahead and solve that, you will see just a quick look here. I just want to make sure, yeah, 4,000, so I have not exceeded, and then I've got just a quick scan here to make sure. What you're going to find is that the distribution is probably going to be equal in most cases, so you don't provide more power than you need to. And we'll hit OK just for the heck of it. Let me go in here while I notice this and format this cell to currency so that you'll know what your cost is. Let me just make sure I did the same thing over here. Format cells, that should be currency. And that way you can compare the cost. But again, this is algorithmic. So just make sure that what you're probably going to have to do is just update these unit costs and probably the demand. But the setup and solver is not going to change. So I hope that one is helpful. The next one is a distribution problem. Interesting here because we got a couple layers. So we've got a supply of, I don't know, let's see, consists of 3 plants. I don't know what we're actually shipping, but we're going from 3 different plants to 2 different warehouses, and then from 2 different warehouses to 4 different customers. And you notice that there is a supply maximum at each one of these plants, and then there is a demand requirement at each one of the customers. I thought it would be easier to lay out the decision variables here just horizontally. I think this one works out well. Notice what I've done here. So each X, notice I've got some X's and I've got some XX's just to try to separate the 2 things that we're doing here. So we're going to have to distribute from the plants to the warehouses. Those are the X's. So this is from plant 1 to warehouse 1, which is 0.4 on the network diagram here. I've actually given you the correct, one of the questions in this problem is choose the correct network diagram. So I have shown it to you here just to make sure that there's no questions. So let's see, so from plant 1 to warehouse 1, plant 1 to warehouse 2, plant 2 to warehouse 1, plant 2 to warehouse 2, and I've put the nodes on here instead of trying to confuse warehouses, plants, and customers. When you get over here to the XX, this is from 4 to 6, so warehouse 1 to customer 1, warehouse 1 to customer 2, so on and so forth. So that's how I have listed my decision variables. And then I have provided, it looks like these are unit costs for shipping a unit from either a plant to a warehouse or a warehouse to a customer. And so let's look at the constraints here. So there's a number of constraints. Notice, let's see. So these first 3 rows represent the supply constraints at each of the plants. So notice I have picked out here, and I had just put coefficients here. The coefficient on X14 and X15, what is going to be computed over here is the number of units supplied from plant 1. This line will compute the number of units supplied from plant 2. Notice I have changed the coefficients to align with those variables. And then this one is the number of units shipped from plant 3 to the warehouses. And then I have picked up those variables by putting 1s here. So those should be fairly straightforward. I have equilibrium 1, equilibrium 2. Let me get to those in a second. The next thing I have here is I have the customer requirements at each one of those. So at customer 1, 2, 3, and 4, the requirements respectively are 300, 300, and 400. And notice what I have picked up here. So at the customer 1 can receive units from either warehouse 1 or warehouse 2. Customer 2 can receive units from either warehouse 1 or warehouse 2, and so on and so forth. So that's how these coefficients pick up the variables. This one, so these equilibrium constraints, what these are saying and what they are computing is that the number of units that are shipped from the plants to the warehouses have to be, in fact, equal, so that we can make sure that when we go from the warehouses to the customers, that I have the amount of units there that I need. So what we're saying here is what I have done. So if you look at these constraints, effectively what we're saying here is that the number of units at warehouse number 1, or which is node 4 here, is equal to the number of units that are shipped from plant 1, plant 2, and plant 3. So when you set these equal to each other, what you get when, again, this is one of those algebraic steps where you subtract the coefficients to the left-hand side, some of these are going to turn out to be negative. And then you'll get the same thing here. The number of units that are shipped from, let's see, warehouse 2, which is node 5, has to be equal to the number of units that come into warehouse 5. And you'll see I have 1, 5, 2, 5, and 3, 5. So again, these are just equilibrium constraints. And again, just saying that I can't ship more from these warehouses to these customers than I receive as the input. And again, this is just one final algebra step. Okay, to wrap this up quickly, I have, let's see, 4 suppliers. This is 1021, by the way, 4 suppliers that can produce some number of products to a variety of 4 distribution hubs. And what we want to do is we want to minimize the cost of getting materials from 6 potential vendors to 4 potential distribution hubs. So similar to what I did on 10.7 with the power problem, I have set up the decision variables in line with this matrix where I have the dollar values, right? And so we're going to minimize cost here. This again is our old friend, the sum product of the decision variables and the cost per, I believe that's cost per thousands. Let's see, I guess that's the total cost in thousands of dollars of the order that would go from each one of the 6 distributors. Now, there's an interesting twist on this one. Notice that I have 6 suppliers and I have 4 distribution hubs. So ultimately, 1 of the or 2 of these bidders will get left out in the distribution process. So there's 2 constraints that I need to satisfy here. I need to make sure that each one of the providers only provides to one of the distribution hubs. So what I'm computing here is I'm computing the sum of all of the Martin opportunities, and that has to be less than or equal to 1, and I have done the same for all 6 distributors. The next thing I have done is to make sure that each one of the 4 distribution hubs gets a shipment from one or the other of the 6 producers here. So I am computing here the sum of all the values in this column, which would be whether or not I get a distribution from Martin, Schmidt, Miller, so on and so forth. And because each one of these has to have a distribution, I'm setting these equal to 1. Remember, I said there are going to be 2 companies that get left out here, so I have set these less than or equal to 1 because they do not have to be 1 in the final, in the optimal solution. So from a solver standpoint, I am optimizing, I'm going to minimize cell 29. The decision variables, again, are these 24 cells that I have listed here. Very clear on the constraints. The providers, which is, let's see, 33 through 38, must be less than or equal to 1. And then the distributors must be, each of them must be equal to 1. I have added one constraint here to say that my decision variables in this matrix right here must be 0 or 1. They must be binary in order to make sure that we are able to compute the decision or compute the optimal solution and make sure that we satisfy our constraints. So folks, I hope this is helpful. If there are any questions, please reach out and have a great week and God bless.